All right. So, yeah, thanks, Matt. So, as I mentioned, my name's Kevin Jones with Capstone Technology. We're talking about Data Park. Today, the title of the presentation I've chosen is The Digital Twin to Empower Your Resources. So, kind of what that means in our world, the things we'll go through. We'll have a little bit of fun first. To get into, what is a digital twin? So this is sort of the fun part of it. And then, like we like to do, we're going to get practical and talk about, what is important about a digital twin, what are some of the use cases around that, and then from a Data Park perspective, what are some ways that we can provide information, provide software technology, kind of in the realm of digital twins to solve some problems. So let's go ahead and kind of walk through these 4 parts here, and starting with, as I mentioned, kind of the fun part of this, the idea of a digital twin. So one thing I looked at, I was just curious around the popularity of the term. Is what you're seeing here is it's Google's search popularity over the last 10 years worldwide for the term digital twin. So you can see that somewhere in 2016, early 2017, that term started to take off, and we're at, relatively speaking, peak search popularity now. So this kind of reinforced kind of my thoughts that it's a fairly new term into what we're doing. But what I kind of took a step back and then looked at all of Google's history for the term. So they go back to 2004 when they started tracking this, and you can see that actually it was a term that had a little traction nearly 16 years ago as far as search popularity goes. So while because of I think a lot around the hype around Industry 4.0, Industrial Internet of Things, some of the kind of key themes we've been hearing a lot about in the last 4 years, the digital twin's taken off. It's not a new term by any stretch, which really reinforces our belief with the Data Park software that these tools have been around a long time. These problems are not new. We certainly have some new technologies to make them easier, to make them cheaper, make them more available. But the problem's been around for a long time, and people have been trying to solve these problems for a long time. So there's a company that's been doing this for 20 years now. I think we've got a lot of interesting ideas and concepts around this, which kind of this shows that this is a problem people have been trying to solve for a long time. So that's kind of the history of the term. The other thing I was trying to figure out is there a definition of what a digital twin is? What are we really talking about here? So I went to Wikipedia. And they had a couple of definitions in the Wikipedia page. The first, this really, elaborate, specific definition where it says a digital twin is an integrated multi-physics, multi-scale, probabilistic simulation of an as-built vehicle or system that uses the best available physical models, sensor updates, fleet history, etc., to mirror the life of its corresponding flying twin. So there's a lot there. Which to me means a highly sophisticated flight simulator, something that not only has the sensor data related to the plane, has the control systems related to the plane, but has built-in first principle physics models. So something that takes a lot of time to build, very expensive, and very specific to the asset. A flight simulator for a 737 is very different than one for a Boeing A380. So I think this is on one end of the spectrum of what we talk about when people mean a digital twin. But we look a little further in Wikipedia. Wait, there's more. Definition number 2: a digital twin is a real-time digital replica of a physical device. So a much shorter and simple definition, but also quite general and broad. This could be interpreted as something as simple as an HMI process graphic that represents an entire unit operation. So, where you have all of the digital sensor data for a unit operation in a display. So we can see that it's a very broad spectrum when it comes to the digital twin solutions. The highly sophisticated flight simulator solves a very specific problem, and one that people can invest a lot of time and money into. A process graphic or an HMI display that shows all of the key data for your process solves an entirely different problem. Much easier to do, much cheaper to do, but not as sophisticated. So there's a variety of solutions, and there's a spectrum in the middle of what we want to provide with our digital twin. So the key is, what problem are you trying to solve, and then finding the technologies related to that. But one of the keys that we see there is the ability to have access to the data. And while it's not a one-size-fits-all solution, providing a common platform to access data related to the plant is one of the common themes. And so that's what we're going to talk about in the kind of the perspective of Data Park, in the keys for us when it comes to digital twins. So there's three other things that we think are really important. One is we want to make sure these tools are used by everyone. So it's not a niche product that just a couple of key stakeholders in an organization are able to fully leverage and fully take advantage of. Oftentimes when we see customers that are doing some sort of digital technology, oftentimes homegrown or kind of a pet project. One or two people are really good at it, but the rest of the organization is not. We want to make sure that we can empower the entire organization to make decisions with data. Number two, easy. We want to make sure it's easy to implement, easy to roll out, and easy to train. That's really one of the key elements to making these projects live. And the other key element is making sure it's pervasive, so that we're able to institutionalize data-driven decision-making and become a real core part of the culture of an organization. So let's get into a little bit more examples of what this means from a Data Park perspective. One is, I think, the idea of our common theme around the data platform. So no matter where a data exists in an organization, the Data Park platform can plug into it. So for many of you, being GE historian vendor or customers, that would be a core part of the data. It could be GE's plant applications, or it could be another lab quality system that you have in the plant, a manufacturing execution system, again, plant applications or something else, ERP, shift logs. And something we'll talk about here later in the presentation could be standard operating procedures that you have out there. So most organizations have some kind of data infrastructure out there. We want to make sure that we can tie that all together and eliminate these data silos. So where we're going to go next is a couple of use cases from the broad standpoint. And within each use case, we've got a couple of Data Park examples where we're trying to solve a problem in relation to that use case. So the first use case is the idea of empowering remote subject matter experts. And I use the term remote in quotes here because a lot of people are remote SMEs these days. Historically, kind of referred to corporate resource that supported many of the plants out there. But today, and I think in the foreseeable future, we're going to have a lot of people working remotely. So how can we make sure we have the digital tools to solve those problems effectively? One of the diagrams that we like to show when it comes to this is the idea where you have a couple of plants with that have data associated to them, somebody who's supporting those plants as this remote process expert, and then a uniform set of content for each plant. And in many cases, plants could have different sources of data, but a common set of content. So we talk about corporate uniformity and site flexibility. So if sites have different data systems, that's fine, because we can plug into any data source without double storing the data. we can create that uniform digital twin content. We recently did a project this last year with one of AutomaTech's customers in this use case. So it was a remote operating center where they had people in North America in one location operating plants across North and South America. So this concept certainly fit their world, and we asked them if they would share a picture of their control center just so people can get a sense of it. And they said, yeah, no problem. This was the picture they sent us. So this actually happens to be NASA's Mission Control Center, not their remote operation center. But I think the idea holds true that NASA Mission Control is an example where remote experts are helping to operate an asset, and they need all the information associated to it. So we've certainly achieved similar objectives on a much less critical scale, but the idea is the same. So now what I want to do is get into a few of our data park examples. So let's get really practical here. So this first demo example, these were videos recorded by the Chief Technology Officer for the data park product, Ron Baldus, where he serves as a consultant with some of our customers. In this case, they're having an issue with boiler efficiency. And the question they were asking is, how long did this problem last? That was the first question they wanted to answer. So let's kind of see the data park system in action to answer these questions. So the first thing that he's going to do is he's got the Park View application open. He's going to go to our tag browser. So in this case, we are linked on top of an existing data historian. There's, if you roughly follow the mouse here, 35,000 tags in the historian that we're linked into. He's curious about boiler number 9. So in our search bar there, we're going to start off with typing BLR. So that's the nomenclature that they used for the boiler. And now we've dynamically shrunk the list to just 175 tags. We have data from mini boiler, so we can use the wildcard character, the asterisk, and then type in 9 so we can get boiler 9. And now we're down to just 41 tags. Alternatively, there is a process filter over here that he could have clicked on to search, but this just kind of highlights the real ad hoc self-service nature. You don't have to build out your asset model first. You can just take advantage of these things in an ad hoc nature. So now we're looking for the flow data that we were interested in. So he types in FT to get the flow transmitter. And for efficiency, we're concerned with the fuel and the steam flow. So he's going to grab the 2 fuel tags, gas and oil, and then the steam flow tag. So highlights them, clicks the trend button, and now we see a trend of those. So the first thing that you can tell right away is the oil flow doesn't seem to change. We go to 30 days, the oil flow doesn't change. So I'm just going to hide that one by clicking on it. Now the next thing that he's going to do is because we know that for a given efficiency, for this same unit of gas flow increase, we're going to get the same increase in steam flow. So he could have built an efficiency calculation, but instead he's just going to use some of the built-in tools of the trend and solve the problem visually. So he just overlaid them. So he put them on a common y-axis and overlaid them. And as you would expect for a given efficiency, you increase gas, steam's going to increase. You decrease gas, steam decreases, and relatively speaking, it happens relatively the same. So now we want to go back, look at a couple of years of data. So the first step is we're going to make hourly averages just to smooth out the data. And now instead of looking at 700 days of data, we're going to look at first 3 days, 700 days. So almost 2 years of data. And now in just a couple of seconds, those 2 years came back. And now visually, you can see real clearly where that efficiency change happened. So he's going to zoom in there. So now for a given unit of gas, we're getting a lower unit of steam. So highlight and zoom there. Now again, our question is, how long did this efficiency issue last? So he's going to drag the x-axis there and start to see where the deviation occurred. And you can tell that's right there around June 15th, June 14th. And just going to use our zoom mouse here to go to the start of this outage. So we can see about the beginning of the outage when things started to get better and the efficiency lined up. And looking at our numbers there, about 57 days. So in a couple of minutes, was able to look back and see how long this efficiency issue lasted. And now I can start to go and ask the next set of questions. Why was it? What other kind of problems may have been solved? So just again, a real simple ad hoc example of solving a problem. So we didn't have to build any sophisticated models or anything else. It just layered on the historian, and these tools work. So next example is again related to a boiler, and in this case we've got a faulty steam flow measurement. And what we're going to do is we're going to create a virtual sensor to continue operations. This way the operators can continue to operate the boiler, not have to take an outage or put in a work order to see what the steam flow coming out of the boiler is. In this case, we'll highlight our multivariable modeling tools, again, in a very ad hoc, self-service way. So this. So the first thing you can do, this is our graphic that they're starting off with, is go to a pre-built trend related to the boiler. And this upper left-hand trend, the green line, that's our steam flow. So we can see that the steam flow is dropping periodically. And the first thing he did is ask the question, well, is it the sensor or is it the actual boiler changing? So by looking at the other tags associated to the boiler, you can see that everything else is pretty steady. So, if that steam flow would have actually dropped, some of these other sensor values would have also dropped. So we know that it is the sensor. So that was the first question that he asked and answered. And I was like, okay, well, I really want to build a virtual sensor for the steam flow. So the operators have some visibility to what's going on. So that's where we're going to go next. And kind of the next thing is, let's add some other tags related to the steam flow so we can build our model. So we're going to go 7 days of data. Add a couple other tags that we think are going to help us model the steam flow. Add those to our main trend. And off the trend, we have this right-click Park Model. That's our multivariable modeling tool. And that took the 4 inputs and the output and built a model. So we can see that we have an R squared of 0.9, so a very good R squared. So our model fits really good. And then our importance down here in the bottom, the 4 inputs are all about 25% important. So we know they're all significant statistically for the model. So that gives us some confidence that we've built a good model. And now what we can do is go in and create a trend of our model. So we'll launch our prediction trend in the dark green aqua color. That is our virtual sensor for the steam flow. So he's going to grab that calculation and add it back to our trend that had the actual sensor on it. We'll change the color so we can make it stand out a little bit. Instead of being that dark aqua, we'll make it red. We'll put them on the same y-axis. So the green tag, this is our steam flow sensor, and the virtual tag are on the exact same y-axis. Get rid of our other tags. And now we have our virtual tag laid on top of the actual sensor output. So now when we zoom in on an area where there was an issue with the steam sensor, our virtual tag can come into play. So what he's going to do now is he's just going to hide that red tag so that it's not there. And so during normal operation, the operators can look at the actual steam flow. But if that's having an issue, they can just uncheck the red tag, and the virtual sensor will come into play. So it's a very simple example of a practical solution to a sensor having a problem. So in a matter of, again, a couple minutes, we built a virtual sensor to give real-time feedback to operations for a sensor that's having some problems. So again, another very self-service way of building, in this case, a digital twin as a sensor estimation for a virtual sensor. So use case number 2 is kind of broadly what I call a digital knowledge base of the plant. So really the goals of this provide effective training. So as you bring on new people into the plants, we can have information about the plant that's really helpful for them to know what's going on. Create a real, I think, effective knowledge transfer shift to shift. So if we have, common content that each shift is using and have really a common language that we're articulating throughout the plant, that helps. With the ultimate goal of, making everybody a process expert and helping, eliminate the troubles we see around the brain drain. So if we can incorporate the knowledge of people who are leaving our operations and know a lot about the plant into a digital technology, then we can transfer that very easily. So the first example that we're going to highlight in this idea uses our high performance process graphic. So that's a graphic that has all of the information related to a unit operation. And many times the high performance process graphic is the equivalent of many different HMI screens. So it's at a higher level than HMI. In this case, the question that we're trying to answer is, why is the boiler oscillating? So we were told there was an issue with oscillation on the steam output of a boiler. So we're trying to figure out, well, why did that happen? So let's go a bit here. And so here's our high performance process graphic. So we've got the steam generation and all the intermediary steam headers, as well as the final consumers of steam. So this boiler steam flow output is where we had the problem. So number 9 boiler. We knew the problem occurred back in January. So we're going to go to a 30-day trend, and then we'll pan back a couple of 30-day periods. So we get to where the oscillation occurs, and then he knew that it is right there around January 18th. So he's just going to highlight that period there and zoom in. So sure enough, we see the very periodic oscillation occurring there in our steam flow. So now we need to investigate, is the boiler itself causing the steam issue, or is it something downstream of the boiler that is causing it? So first thing I'm going to do is look at just a little bit more data. In this case, we're going to do a 3-hour time window and kind of get it to a very representative period. So just drag the x-axis a little bit, and we can see that representative period. And now let's add some data from our process graphic to do our troubleshooting. So this is a benefit of having this process graphic. The data that we want to do for troubleshooting is right there at our fingertips. So the first thing he's going to look at is another one of the boilers. So we've got number 9 and number 11 boiler. And again, we're going to use just the y-axis dragging up and down to see. And so he just overlays the two by moving the y-axis for boiler 11 up and down, and you can see very clearly the same period. So if we have 2 boilers on the steam generation side oscillating on the same frequency, we know that it's not one boiler. It's a problem downstream in the steam network. So we now know it's not number 9 boiler is a problem. It's something downstream. So it could be one of the final consumers or something in the middle. So we've got an 800-pound steam network. We've got a 160-pound steam network. So let's figure out where that problem's occurring. So we're going to start with the pressure reducing valves that take us from 800 pound steam to 160 pound steam. So there's two of them. So number one, flat. So that's not the problem. So you just got rid of it. The number three PRV has a very similar oscillation. So if we use the the same game visually, we can see that that's probably a problem. And it's also going to go down to some of the final consumers of steam. So in this case, we've got machine number one that we'll look at the steam flow for. And then we'll go to machine number 7 and bring those over. And so visually, it looks like they are, but we'll kind of play this, we do the same idea of the y-axis moving. So we've got number 7 at the top there, and he's just going to take number 1 and move it over the top. And visually, pretty clear that machine number 1 and machine number 7 are oscillating on the exact same frequency. So just like we kind of deduced with the steam generation side, if there's two final consumers oscillating together, it's the chances of one of them being the culprit are really small. So it's got to be something in the middle. Most likely are that PRV3 that's the problem. But now just to verify that our eyes are correct, we have a fast Fourier transform chart here. So let's go to the FFT, and now we see the actual period for all 4 tags, and it's very obvious that at about 7-minute period, all 4 tags are oscillating on the same frequency. So we know it's not the generation side. We know it's not the final consumer side. It must be somewhere in the middle, and so the number 3 PRV is our culprit. So from here, now there's still some more work to do. Is it a tuning problem? Is it stiction in the valve? We don't know, but we have deduced or reduced the number of things to look at significantly to now go solve the problem. So in just a matter of a few minutes, we went from is it somewhere in this huge steam network the problem to we know it's PRV3, let's go solve the problem. And again, we didn't have to, other than building the initial process graphic that can be reused for lots of use cases, we didn't have to build any real sophisticated models or advanced analytics. It was all just right here. So the last demo example I wanted to show is the idea of our kind of our online knowledge base. So the idea of integrating the knowledge of your process experts into DataPark, so you can find your information easier and have it available to everybody. So in this case, I'm going to be the one driving here, and I'm going to go to our demo system. So this is another trend related to a boiler. In the top left, we have some of the output of the boiler, so the electricity from the turbine, some of the steam production, the actual boiler bed. Then I have some environmental data on here. So in this case, this is sort of an environmental use case where we're having some issues with our TRS, our air emissions. And I'm new to the plant, and I'm not sure what to do now if I'm having issues with TRS. So if we right-click on the tag, we go to the 5Y here. So this is our online knowledge base. So this is data that's been associated to TRS to help me solve that problem. So I have a series of other process tags, in this case, the fuel flow and the air flow to the boiler. Those are associated to my TRS, but I also have other documents. As I mentioned kind of at the beginning of this is where standard operating procedures can come into play, where we can have a link to our standard operating procedures that anybody can access. We could have a link to other dashboards, training content. In this case, it's just a URL to Wikipedia, so it could be an internal intranet site. So it's just putting, in your visualization tool, links to all of the content that you need to solve a problem. So as the new person in the plant, what I'm going to do is I'm going to launch the trend of the associated tags that I was told are important. So here we have the TRS, and here for the same time period, we have a trend of the actual fuel flow, so the coal flow and the airflow to that boiler. So to kind of help navigate a person down the road to solve a problem. So that's another kind of example in our world of digital twin content that we can create that you can easily use and reuse in your organization.
Hey, Kevin, let me jump in here because we have a couple of questions, and in the interest of time, I want to keep going.
Yeah, which is good time, as I am done.
Okay, all right, perfect timing. So one of the questions that came through, I think this one actually popped through while you were covering your first or second use case. It was really around the, we'll call it the, the tag and data connectivity. So Christopher asked, how many signals can be layered along when you're doing, signals or tags can be layered along when you're doing this deep analysis? Any limitations, any scalability things you could talk to?
Yeah, so the trend itself supports more than you would ever need. It supports 1,000 pins per individual box trend. From a practical standpoint, 8 to 10 is where we usually see. But I think the question is more important on performance. We have an acceleration engine, a performance data engine that helps speed that up. So we have a lot of cases where people will have 60 or 70 tags per multi-box trend and looking at months of data. So we can scale pretty high and still perform really well with the trend.
Great, thanks for clarifying. The other one to ask here is around GE Historian. So an example case is if someone has a GE Historian in place, what does it take to connect to the GE Historian and start building out some of those trends and ultimately building out some of those data models that you showed?
Yeah, not much. So we use the API provided by the GE Historian. So we can be installed, hooked into the Historian in a matter of hours. And that API gives us access to all the tags you've configured, all the history that exists inside the Historian, and then just a matter of providing some training and to be off and running. So our projects are, we look at a matter of days to be implemented and off the ground and running.
Oh, great. Good to hear. Thanks for clarifying that. And there's actually a somewhat related question that came in here as you were answering that is regarding the park model data results. Can they actually be written back to a GE Historian?
Yeah, they can be.
Awesome.
Yeah. So those are our calc tags, and then we just set up a job to write them back to the Historian. Yep. A good question.
Very cool. We have a couple more, but I think just in the interest of time, we're going to wrap up here. So if there's any additional questions for Kevin, please follow up with us, your AutomaTech representative. That was good stuff, Kevin. Great to see you.
Yeah.
You guys are doing data analytics. Hopefully it was helpful to the group. So thanks for that.
Hey, thanks, Matt. And so thanks to everybody who joined today. And if there's any more questions, reach out to AutomaTech and we'll be in touch.